All right, welcome back, guys. Let's continue our discussion with chemical equilibrium and K. We're going to be looking at K expressions again. This is just making sure that it's in a slightly different format than what we've talked about before. So I'm going to go ahead and share my screen. That way you can see what I'm talking about. And let's look at a Kc value from data. Okay, we have done this. We've calculated this a couple of times. But now we're looking at it in a slightly different way. Okay, we're looking at the relationship between H2 gas and I2 gas to give me 2HI. So I have H2 gas plus I2 gas, giving me 2HI. And what you may notice is that there's this table underneath that, and it's got a couple of letters that are written on the side. So this is labeled as R. R stands for reaction. And so you'll see that it actually says reaction in the slides itself. So it's a reaction right there. Our next line down is listed as an I, and that's for initial. We then have a C, which stands for change, and an E, which stands for equilibrium. Now, we're going to talk about Rice tables and or ice tables, depending on what you call them, in detail in a few slides. But I want to bridge the conversation to say we can calculate a K just like we've been doing by using one of these tables. I find that students don't necessarily understand that this is the same deal as what we've been doing, and it's really no different, okay? So we look at our concentrations for H2 that we were given initially. 1.0 times 10 to the minus third, 2.0 times 10 to the minus third, and then 0 for our HI. Okay. We're going to skip this change bit. I'm actually going to leave it out of the table that I'm writing because right now we don't need it, and we'll talk about how that comes about and what it looks like in a few slides. But we want to focus on the equilibrium concentrations. This 6.50 times 10 to the minus fifth, 1.065 times 10 to the minus third, and 1.87 times 10 to the minus third. And you probably noticed that I need more space, so it keeps, my table keeps elongating as I go. It's better if we have more linearity, i.e. more space between the H2 and the I2 and the 2HI. But okay, fine. So those are my equilibrium concentrations. Now I know for this reaction that my Kc is going to be equal to HI, the concentration of HI squared, over the concentration of I2 times the concentration of H2, H2I2. Okay, and I have values that I've been given here. I see that my HI is 1.87 times 10 to the minus third, and that's going to be squared. We're going to divide that by 6.50 times 10 to the minus fifth, and 1.065 times 10 to the minus third. Badly written, not enough space. Yeah, I know. If I do that math, then I end up with 50.51. And I'm including 4 significant digits because most of the numbers that I have in equilibrium are listed as 4 significant digits. Now, initially, we only had 3, but the answers that I've been given are 4. So I'm going to say, okay, fine. I'm going to take this as 4 sig figs, and therefore I'm going to list it as 50.51. Okay? So that's the answer that I get from that math. Now, is this any different than what we've done in the past? No, absolutely not. We squared our HI, we divided by the H times the I to the first power. This is exactly what we've been looking at for the last couple of things. So let's reconsider some K values, all right? And here we're going to be doing some manipulation with K expressions. So it's not just what we had previously. We're going to consider how we deal with this. Now, we calculated an NH3N2 plus 3H2 concentration previously. So the K value for that we calculated. And at 500 degrees, we had calculated that to be 5.9 times 10 to the minus 7. Okay. Now, and I'm going back and looking at my work so that I can remind myself what that value was. I'm going to take this Kc, which is for that reaction that we're talking about, copy that, and move that to this thing that I'm looking at here. Put that here. No, I don't want that there. I want that there. And then I'm going to say, okay, this was for 2NH3 goes to N2 gas plus 3H2 gas. And I'm going to go back just to verify that that's the equation that I was looking at previously. Back to the previous page, and we have 2NH3 goes to N2 plus 3H2. Okay, again, this is at a higher temperature, but that doesn't matter. So at that temperature, let's talk about this. What does this K value mean? 5.9 times 10 to the minus 7th. What's favored, product or reactant? Well, that large K value, K being greater than 1, means that this reaction is forward in the forward direction. Okay, we have way more product than we do reactant. Forward, reverse, favored forward. That's what we call favored forward. So that because of the value, we know that it goes forward more. So it's said to be favored. Okay. This next one that we're going to look at is that same thing that we did before, that A gas plus 2B gas to give me 3C gas. And yet we calculated a value for that right here, the work that we did on the previous page. And it's hard for me to highlight things. This is the reaction here. A plus B, 2B goes to 3C. We calculated K for this of 0.835. So I'm going to copy that. I'm going to go to my next page, and I'm going to say that that value goes here. And again, question becomes, with this value being what it is, what are we looking at? What's favored, what's not favored? From a very slight standpoint, we know that this prefers to be this way. And I say that because it's just below 1, okay? So I know that I'm going to have more reactant than I do product because it's below 1, but it's not that big a deal, okay? So I'm going to have more reactant than product. And that's again because K is approximately 1, but it's actually smaller, okay? So that's where the logic comes from that I got that. Now, let's talk about our next one. We had 3A aqueous goes to 5B aqueous plus 2C aqueous. And since I don't want to have to keep flipping back and forth, I'm going to do the 2NO gas N2 gas plus O2 gas. And all I want to do at this point is go back and get those values. Now I'm going to have to flip back and forth anyway. So again, the next equation we're looking at is that 3A. Sometimes it will do it, sometimes it won't. So again, we're looking at this reaction right here, which we calculated K for of this one. All right, I'm going to copy that. Move this over here. I'm going to put that down. And it won't do that again because I didn't want it highlighted. So 2.41 times 10 to the minus third. Oh, 10 to the minus 2. Okay. 10.41 times 10 to the minus 2 is less than 1. So this is k is less than 1. That means that I favor that reaction going backwards. I favor my reactants, more reactants than product. And the last one we had previously done was at 2NO. So 2NO plus N2, this last one that's written here, the answer that I got for that calculation is 2.5 times 10 to the minus third. Yeah, garbage. Again, that's my Kc value for this. 2.5 times 10 to the minus third is still a Kc less than 1. That means that we're going forward the backwards reactant. We're going to have more product, or sorry, more reactant than product. So now that I have some values, I want to think about what is that practical application. So where does that equilibrium lie based on the number that I was given? Okay. Any questions about that? If we have questions, comments, problems, concerns, anything, let me know. Again, I can make these slides available to you if you are looking to see them. I'm going to stop sharing and I'm going to set up for the next recording. So hopefully I'll see you back here in a few minutes.